Alright, so we left off on número 21. So a transverse periodic wave travels along the string that is stretched along the x-axis. The figure above shows the y position of a point on the string as a function of time. What further information is needed to determine the wavelength of this thing? So, before we get into it, what kind of waves do we have? We have two kinds of waves. Transverse and the longitudinal. What's the difference between them?
Longitudinal is sound, isn't it? No, it's the one that...
Well, longitudinal is sound waves, but what's the difference between a transverse wave and a longitudinal wave?
Longitudinal is like this.
Yes, longitudinal is like this, but...
It travels to the parallel to the...
Yeah, longitudinal travels parallel to what? Well, the medium moves parallel to the wave. And the other one, the medium moves perpendicular to the wave. So the wave will be moving this way, but in transverse wave, the medium's moving up and down. So let's look at 21. Transverse wave. The figure above shows the y point of a point on a string as a function of time. What information, if any, is needed to determine the wavelength of the wave? Alright. So what are you guys thinking for this one? With the answer choices.
I feel like we need the frequency.
He says that you need to know the frequency. Why would you want to know the frequency?
If you know the frequency and the wavelength, you can find the speed.
Okay, let's look at what Daniel just said. If we know the frequency and the wavelength, we can find what?
The speed.
The speed. Yes. Yes. What are they asking me to find though?
The wavelength. You don't need
They're asking me to find the wavelength.
We don't need
Not the
though,
speed.
right?
So it's actually the...
Is it D?
It is D.
You don't need anything.
Well, we do need... Oh, no, sorry.
Well, to find the wavelength, though.
Oh, sorry, no. I thought the answer was... The answer I was thinking I thought was D, but no, it's not D. Like,
No?
no.
What is
I
the
thought
y
like
axis?
you were saying.
So,
Well, what information... Megan, what information are you getting from this graph? What can we...
Period. You get the period.
You can get the period from this graph. And from the period you can get...
frequency.
So we do know the frequency from this graph.
If we know the frequency, we know the velocity.
Velocity.
We need the velocity to find the wavelength. The answer will be A. Because we do from this graph, they wouldn't give you a graph if they didn't want you to use it. Graphs are never going to give you extra information. Graphs are never going to give you extra information. They're going to give you something. In this case, they give you the frequency. 22, oh my gosh. 44%. 44% got this one right, number 22. And that is way too low of a number. I expect all of you guys to get number 22 right. Go ahead and do number 22.
Shit.
Well,
At this point, I don't even know. Yes. I don't even know anymore what to say or do if you get this one wrong. And if you do get it wrong, I'm sorry, not to make you feel bad.
Alright. See that I'm gonna get
You mean you should at least cut it down to.
I
You
saw
can't.
why you're saying
I
that
say
he's
it's D.
disappointed in us.
I take that back. If you cannot cut it down to at least these two answers, then I am going to be disappointed.
Should be.
What's the answer? Sorry, Adriana. What is it? D. So when two objects crash into each other, when they collide, which one experiences the bigger force?
They have the same force.
Newton's third law tells us that anytime there's any interaction, that interaction can be collisions or repulsion or attraction, because sometimes it's the electric force between two objects, or sometimes it's gravity. But in collisions especially, which one experiences the bigger force? They both experience the exact same force. So we should have got it down to C or D. And they both experience the same force because interacting objects cannot exert different magnitudes on each other. That's just like Newton's law right there. The answer is D. The mass doesn't matter. The velocities they crash don't matter when it comes to which one experiences the bigger force. Now, if they're going to ask you which one experiences a bigger velocity change afterwards, the one with the smallest mass or something like that, which one experienced the bigger change of momentum, then we can do something like that. But the force will be the same for both of them. The time will be the same for both of them. Also, this leads me to impulse momentum theorem. In a collision, both objects experience the same force, and they're in contact with each other for the same time. It almost seems funny to think that they would experience different times. I mean, touching the table right now. Who touched the table? Did the table touch me longer, or did I touch the table longer? I mean, like, right? That's the way to think about these crashes. Like, the time is the same for both, and they both experience the same crash. So when objects crash into each other, me into my son into my daughter, me into Daniel when he's running down the hallway or something, we both experience, in a collision, both objects experience the same impulse. Same force and same time. They're both going to experience the same change in momentum also. Because impulse is change in momentum. The change in momentum will be the same for both. Now when we do MVF minus MVI, these numbers might be different because they both have different velocities, but when we find the difference between how fast they're going before the car crash and after the car crash, or before the collision, after the collision, the change in momentum will be the same because they had the same impulse, the same force, the same time.
So if they have the same mass, like if don't put two of these in the calculator, right? They have the same mass and they're going the same velocity and they crash. We could just fix that.
Yeah. $23, 3 spheres. %, got this one right. But the other problem, 44% getting that one right. That seems low to me. in that last problem. Better than that. Forget the rest of the nation. 3 spheres with masses indicated above are initially far away from each other, and the gravitational potential energy of the 3-sphere system is 0. The spheres are then brought together until each sphere is a distance of r from the other 2 as shown above. What is the new gravitational potential energy of the 3-sphere system? Far away from each other? This makes me a bad teacher right here, and I'm sorry, people in the video. And to you guys, the answer is D here, but I don't want to explain this problem. No, because
Alright.
this problem is very, very unique. If you miss this will not be a free response problem. On the free response, you won't get a problem this complicated. And if you miss one of these 3 particle problems, on the multiple choice, that's just 1 point that I don't mind you losing.
Yep.
I hope that doesn't come back and bite me in the test.
Knock on wood.
Well, you missed on the mock, you missed it by 1.
I know, because when I saw it, I was like, I don't know what this is. Looks like a Illuminati sign. I don't know.
Let's go ahead and do 24. 24 we've seen, I think, like twice already. A steel sphere A, mass M, is moving along. Go ahead and do 24 on your own. We still have liquid nitrogen left over. I don't have any marshmallows.
What? You can freeze marshmallows?
Marshmallows though.
What?
We had 2 bags of marshmallows.
I know, but they're like all the way in my car.
Why marshmallows?
We'll do it later at the end.
Really? Today?
Yeah.
Oh my god.
Okay, we'll do it then.
Honestly.
She has to leave soon. Do problem 24.
Oh.
Take it back. I don't know if you guys can do this one.
Have we gone over angular impulse?
That's why I thought it was just the regular column, but the angular impulse.
That's 2 points.
Because I don't know what
The answer is
Honestly.
okay.
The D?
The answer is D. So when you're talking about angular, you want to know not the angle, the radius, which is the axis of rotation.
Oh my god.
So angular means that there's an axis of rotation, so you need to know what the axis of rotation is. So that it should have knocked out A and B. And then the M and the V, you need to find the velocity of B. Once you know the velocity,
can determine how high it went.
we're not trying to determine how high it went, we're trying to determine the angular impulse. But to find,
the height, can't you from there determine the angular impulse?
well, no, because you don't know what angular impulse is, so I'm not mad. Are you saying this? But the impulse is the what? the impulse is going to be IW,
Oh, IW final minus IW initial.
or just IW.
What do we do with MV?
Yeah, MV. In order to find W, you need to know the velocity. That's going to be the velocity of the B. So there's going to be a collision here. So you need to know the velocity at which the other one is coming at. So that's why you need to know NV of A. It's
So
a,
is this assuming that A was like rolling and then it like crashed into B?
yeah.
Oh.
So you need to know the MV of A to calculate the W of the other one. And then I depends on, yesterday we said, not only the mass, but I equals mr squared. Where the bigger the radius, the smaller the inertia. So we would need to know that.
Are we still on 24?
Yeah.
Okay.
Sorry. I thought it was like a, how high is it gonna go problem.
Yeah, it's I was thinking kinetic potential.
Yeah, I was like, kinetic potential. Nah, I gotta read these problems. Alright, let's read this one, let's see if you can do it. 2 problems in a row, not looking good for me. A 1 kilogram block is attached to an unstretched spring, a spring constant of 50 meters per second. Sorry, 50 newtons per meter, and released from rest from the position shown above. The block oscillates for a while and eventually stops moving at 0.2 meters below its starting position. What is the change in potential energy of the block Earth system between figure 1 and figure 2? Dang, you guys can do that one, I think. What is the change in potential energy? That was something. Change in potential energy. What's the equation for potential energy?
Not spring potential?
Oh, okay, I see what you mean. Keep working that out. I'm curious now.
I didn't do it right.
Gosh.
Why?
Because I was gonna do the final, the initial,
Uh-huh.
but I don't know what's initial.
Well, what does the X stand for? The X is not really a
Oh, it's
distance.
displacement, since here,
Yeah.
and then, oh, okay, well then that's different.
So let's go ahead and bring this one back.
Shit.
I can see where a lot of kids made mistakes. This one was 28% right.
Is the answer 8?
The answer is A.
Yes.
So, we're looking at the change in energy.
Oh, cool.
And what kind of energy do we have right here?
Spring potential energy.
Spring potential energy. And what's the equation for that?
1/2
1/2
kx squared.
1/2 kx squared minus 1/2 kx squared. Final and initial. So we have 1/2 50. And what was the displacement?
0.2.
No, it was the answer, and then it can't be eight.
Is it A?
That's why.
Because the initial minus
My mind is blown right now.
So
This
what,
test went from like easy first half to like blowing my mind second half.
so
So
what's,
Wait, so it's C then?
that's not what Google says. 0.2.
No, because you get that. It doesn't have to.
Why does it
doesn't
start
have
off with a negative
displacement?
0.2?
What?
Doesn't it have a negative displacement though?
Yeah.
Does it put-
When you square negative, it becomes,
Positive.
yeah. Just like kinetic energy can't be negative. We all got that right though? I bet a crap ton of kids put C.
I feel like I put C at the test, but right now I just.
So I wrote look into, because this one is boggling my mind. We all got the right magnitude though, right?
Yeah.
Right magnitude?
Yeah.
Cool. I'm really gonna look into that one. So, 26, block A and B of mass M and MB are at rest on a frictionless surface as shown above, with blocks A fixed to the table. Block C of mass MC is suspended by a string that is tied to block B over an ideal pulley. Which of the following gives the magnitude of the force exerted by block A onto block B? Go ahead and try this one on your own. We're looking for the force of A onto B.
Oh.
You got it? That's good. What is it? a good problem. It looks really complicated. And then once you figure out what it's asking, you're like, oh, shoot, that's not bad at all. I lost my questions. Oh, they're over here. You got it?
I think I do, but then at the same time, it's like,
What do you think? D? That's if you were finding the acceleration of the system. So, what do you guys get? Let's talk it out. Let's talk it out. So, what can you tell me about the force A is applying a force on block A is applying a force on block B, right? What can you tell me about that force? The force that block A is applying to B. What can you tell me about that force?
the block B is applying the same force.
Block B is applying the same force to it. Awesome. Awesome. So now keeping that in mind, are you smiling because you know the answer?
Yeah.
What's the answer?
Is it B?
It is B.
Okay.
So now you got to be thinking, what that B is being pulled in this direction by what? By C. And what force, what that tension force, that B is being pulled by this tension. That's a tension force. And that tension force is equal to the weight on the string. So the weight of MC is equal to the tension, and tension is the force pulling on B onto A. So that's why the answer is B. Does that make sense?
Yeah.
Yeah? Are you sure?
Yeah, I just don't really get these problems, but that only makes sense.
So, they said that the force that this one applies onto this one, which is what we're looking for, is equal to this, right? So, what force is being applied this way? So you know it's the force of tension. Tension is pulling B onto A, right? Does that make sense to you? So the force that A pushes back onto B is the force of the tension. Because that's over here, right? And then we look, well, what is the force of that tension? Tension is going to equal to the
Pumpkin, but
to the
something
engine.
inside the pumpkin.
Right here. So that's the mg is equal to the tension. The tension is the force pulling B this way
And
onto
they-
A. Yeah.
Oh.
Yeah. So it's a Newton's third law problem.
And then-
So let's go back to this. We haven't seen one of these in a long time though. Because I saw you did it this way, and then you were starting to do it this way. Where we have this pulling thing right here, and then another block over here. And they might ask you to find the acceleration. So how do you find the acceleration? Net force
over mass.
over mass. And when it's a system, we use the total masses. So this becomes M1 plus M2. And the net force, we have to think about what's the force that's in one direction minus the forces in the other direction. So what's the forces right here to the right?
M1.
The,
M1.
Mass of M1.
Well, not the mass of
Of
M1,
the MG of
the mg of M1, the weight. That's the force. And what's the force in the other direction? That's the force to the right. What's the force to the left? Well, if there was friction, it would be the friction of this one. So it would be minus Does that make sense? This right here is the friction of this one. And that's how we find the acceleration. Now, if there was no friction,
It's just mg.
then it would just be that right there.
Oh.
And we haven't seen one of these in a long time. So I thought is that what how you were trying to solve it? And then once you see right here, you can like pull out the G, and I think that's what you were trying to do right there. So 27, a student shakes a horizontally stretched cord, creating waves. So he's pulling it this way, and he's shaking it, creating waves. The graph shows the vertical position as a function of time. The student then tightens the cord. Tightens the cord, so the tension got higher. We changed something, so what can we predict change already? Something about the speed. Tightens the cord, so the waves will travel faster than before. How should the student now make the cord to make the graph of y versus look the same as above? How should the student now shake the cord to make the graph of y versus t look the same as above? So I'll let you guys think about that one for a little bit. So, what do you guys put? C. What do you put? D. But we know the wavelength of the waves. So, let's look at D. Let's say I have a string from here to here, right? So it is like the guitar one. So I have it stretched from there to here, and I'm doing that, right? When I tightened, yeah, I haven't gone over the answer for this one. Remember the day I was absent? Oh, you weren't here. This is similar to that problem. So when I change the tension of the string, the velocity went up, and then the frequency went up also. So when I tightened it, the velocity changed and went up. And I know the frequency got bigger and not the wavelength because the L didn't change. The L stayed the same in 2L over N. The L stayed the same. So the wavelength stayed the same, so the frequency should have gone higher. So a higher frequency means one further period. A lower period. So if I wanted to make it look like this one, which I would have to shake it in the opposite. So if the frequency went up, it means that the period got bigger. So now I want it to get, if I want it to look the same, I'm going to have to shake it slower.
So, what is it?
I think the answer is A. So this went up. So in order to balance this out, I gotta go with less. Yeah. A.
What is it?
A cart of mass M with negligible friction along a track with speed v1 to the right. It collides and sticks to a cart of mass 4m with an unknown speed to the right. Which of the two principles, conservation momentum and conservation of energy, must be applied to determine the final speeds of the cart? So go ahead and try this one. I'm hoping this one is straightforward enough. This one is. So we're trying to find the final velocity after. Think about what kind of crash we had. What kind of crash C had. And what do we know about that kind of crash? A. What do you put? After today, Hector, I hope I'm just right again. Not that it was like low, because it's not low for any of you guys, but it is higher for some. Just seems like maybe in class you just don't talk as much, but I'm seeing like, I feel like I'm seeing a whole new Hector today.
Just, there's not many people like I'm not tired, stuff like that.
Sleep in the day of the test. Don't come in that morning. Come in energized. I'm just kidding. Don't do that. So, what do you guys get? The answer should be A. Because we know what do we know? We know we can use conservation of energy. Sorry, conservation of momentum. Because we know the m's, right? And we know both these v's. So we can solve for this, because we know this. So for sure, conservation of momentum. Why can we not use conservation of energy?
Because energy is,
Is that what it means? Because it's elastic.
Yeah, elastic collisions have
because energy is lost
conservation of energy.
on this kind of collision.
Yeah, energy is not conserved in elastic collision. Energy is not conserved here, so we can't really use it. We could, but it would be really freaking hard because we don't know how much energy was lost. If they told us how much energy was lost, then yeah, we could do it. Maybe. But it would be a lot harder. No, not maybe, for sure. Because it's inelastic. So go ahead, can't do that problem. I'm gonna, 29, I feel like you guys just need me. It was when the people that did turn in the homework, this was missed all around. I think like only like 2 people got it the right way.
I would have guessed.
No, that's okay. So, because you guys forget this, you guys really do. You always forget about the periods and stuff like that. So, on 29, you're asking us to find the spring constant of approximately which of the following. So, a figure above shows a pole with the spring around it and a 2.5 kilogram block with a hole in the middle hanging from the spring. A light horizontal cord is attached to the block in the wall. The block is oscillating at 10 hertz and the standing wave is formed. A spring constant, the spring constant of the spring is approximately which of the following. So what equations do you guys know for spring constant that have the spring constant in it?
Please, spring potential.
Awesome. I hate that that's the first one, but you know. Spring potential. There's another one.
Is
The
that
biggest
the
one.
law that-
Hooke's law.
Hooke's law. And what is that?
F equals KH.
Kx. So we don't know in both. This one does. We can't really use it because we have 2 unknown variables. I mean, we have 3 unknown variables. We don't know any of them. If we wanted to know this one, we would have to know what the potential energy is, right? Do they tell us what the potential energy is? No. So even if, without knowing this, we can't really solve for K because we don't know X or P. But in this one, we know what the force is. What's the force pulling the spring down?
Which
2.5, no,
The weight.
yeah,
2.5 G. But do we know the displacement? Do they tell us that? Do they tell us the displacement of the spring?
no.
No, so we can't use this one either. There is a third equation that you guys always forget that has spring constant in it.
Maybe there's another one.
The period of a spring is 2 pi m over k.
What the heck?
The period of a spring. Right? You guys tend to forget that one. That also has the spring constant in it. Can we figure out the period from this problem?
Yes.
How?
1 over the frequency.
1 over the frequency. So we know the period. Do we know the mass
Yes.
on the spring? Yeah.
Right.
So we plug in 1 over 10, which is 0.1. 0.1 equals 2 pi over 10 over k, and then you solve. That one is D. 21%. That one was hard. It was hard in that it tested something
That you forget.
really, really unique. Really, really unique. But hopefully you would have gotten the next one, because the next one's a lot better.
Why is it 10 over 10?
What? Oh, I'm sorry, 2.5.
So what was 29?
29 was supposed to be D. After you solve that, you should get D. So, what additional information is needed to determine the speed of the wave? So, there's only one equation for speed of the wave. What is it? Speed equals wavelength times frequency. And I know the frequency, right? So what information do I need to know?
The velocity.
No, I'm trying to solve for
The
the wavelength. So let's see which one of these can help me find the wavelength. The thickness of the cord.
the distance between the unicorn.
So the thickness of the cord, no. The unstretched length of the spring, so we're gonna put that as a maybe for right now. I mean, I don't, because you said it, so like maybe, but read all the choices for me, Hector. The average kinetic energy of the block. Well, no, that would have helped us before.
Wow.
Maybe. Maybe. The distance between the nodes. So let's look at this right here. Where are the nodes? Here?
No,
Here?
Yes.
no. It's like right there. Yeah.
You can't say right there from over
It's
there.
because if you did
So these
in
are
between.
the nodes, right? So if I know that this is 5, can I find the wavelength from here? What's the wavelength equal to? 10. That's why the answer is B.
Well,
What?
I have to go.
Okay. You want us to go get the liquid nitrogen?
Doesn't matter.
Like, I don't know, do you have to go like immediately right now? Like they're here?
No, they're not here. They're just on their way.
You guys want to pause it now? By pause it, we still have to finish the next 10 problems though. Yeah?